Alright, here is a slightly more complicated water lifting problem. We still have a cylindrical tank, but this time the cylindrical tank has been tipped in half and set on its side. So the image now looks a bit like this. Here is a cylindrical tank in the shape of a cylinder that has been set on its side. And the tank has been completely filled with water. So here at the very top, there's water in this entire tank. There's water in this entire tank. Now, assuming that the cylinder that we have cut in half and tipped on its side has a radius of 1, and assuming that the cylinder has a length of 4 meters, how much work would we have to do to empty this tank, assuming that it's completely filled at the start? Now this is the moment where we have got to go back through this process of first of all finding a random slice at a random position to find the area of that slice so that we can find the force on that slice by taking area times the density of water times the acceleration due to gravity. And we also need to find the distance that must be traveled by each slice to escape the tank, so that we can integrate from some lower to some upper limit of the product f of x times d of x. So let's consider trying to figure out what is a of x and what is d of x based on this setup. Now, the first thing to do is to figure out what exactly x represents. Where is x equals 0? Where is x equals 1 in terms of this picture? Now, I'm going to do something a little bit unusual, and I'm going to set x equals 0, not at the bottom of the tank, but at the top. And I'm going to do something unusual as well, and I'm going to set x equals 1 at the bottom of the tank, remembering that this cylinder has a radius of 1 unit, not just in the horizontal direction, but since it is radius, also in the vertical direction. So I'm setting up my coordinate system so that x increases as we move down in this picture, as we move down. So I'm going to now choose a random x value, somewhere between 0 and 1. And I'm going to take a slice out of this cylindrical trough, at that level. And the beauty of having a drawing is that it makes it much easier to see what shape this slice will have. Slice at x will be a rectangle. A rectangle. The slice at x will be a rectangle, and therefore to find the area of the rectangle, I just have to take the width of the rectangle and multiply it by the length of the rectangle. Now this cylinder is length 4, and if you look at this drawing closely, you can see that no matter what slice we take, the length of that slice will be 4 as well. However, the width of the slice is changing as we move up and down on the cylinder. Toward the rim of the cylinder, toward its top, the width of the slice is a total of 2 units. 1 unit toward the right from center to rim, and 1 unit toward the left from center to rim. But the further down you go in the trough, the narrower the slices become. So we have to figure out how does the width of this rectangle vary as we move up and down along this trough. So let's take a side view of this rectangle. I'm going to take a side view of this rectangle. Here is the center of the trough, with 1 unit extending from center to edge, and likewise 1 unit extending downward. And we have taken a slice at a random x value. And here, denoted in gray, is the width of the slice at this x value. Let's see if we can find some formula for the width of the slice at this x value. So here is x equals 0, here is x, and at the bottom is x equals 1. Now, because the difference between 0 and x is indicated by this small line segment here, here's x, we can use some similar triangles by extending a line first from the center of this trough to the edge of this rim here, this edge here. Now, notice that the width of this slice forms a right triangle. I should say half the width of this slice, because we're only dealing with the right half. We have a right triangle where the hypotenuse of the triangle is a line from center to rim of the trough and has length 1. Here is x forming a leg of the right triangle, and here is half of our width forming another leg of the right triangle, which means that I can apply Pythagorean theorem to say that if I take width over 2, if I take that bottom leg of this triangle, that can be found by taking the square root of hypotenuse squared, take away other leg squared. So what have we found? We have found that the width, as it depends on x, is equal to 2 times the square root of 1 minus x squared. And since the area is 4 times the width, the area is 4 times 2 is 8, 1 minus x squared. So now that we have found a formula for the area, we have found practically a formula for the force. The integral from a to b, area function, 8, 1 minus x squared, times the acceleration due to gravity, times the density of water. So it remains for me now, having established the area of each slice, to find the distance that must be traveled by each slice. And I think that this cross-sectional image reveals it nicely. To lift this slice at position x up to position 0, we would need to move through precisely x units to get up to that position of 0 at the top. So each slice would need to move x units. Now, having established the area of each slice so that I get the force required to lift a slice, now that I have the distance that must be traveled by each slice, I can fill in finally the limits of integration. The limits of integration tell you where the water is that you are lifting. So the lowermost water is located at x equals 0. Now when I say lowermost, be careful. I mean lowermost in terms of the lowest value of my coordinate system. So x equals 0 is the lowest x value where the water lives. X equals 1 is the highest x value where the water lives. And my goal would be to integrate 8, 1 minus x squared, g times rho times x with respect to x over this integral.